Good morning everyone. So today we are going to discuss the last chapter of this course, linear algebra, which is eigenvalues and eigenvectors. So let A be a square matrix of order n. Then we say a non-zero vector. Non-zero is very important term. So a non-zero vector x, which is an element of Rn, is an eigenvector of A if Ax is equal to lambda x, where lambda is any scalar. In this case, lambda is a real number. So if you multiply the vector with the matrix A, it is equivalent to multiplication of a scalar with the vector. Then we say that x is an eigenvector and lambda is an eigenvalue of A. So here lambda is an eigenvalue of A and x is an eigenvector corresponding to the eigenvalue lambda. If we see this matrix A, then you can verify by yourself that A times 430 is equal to 2 times 430. It means that for the matrix A, 2 is the eigenvalue and 430 is the required eigenvector corresponding to the eigenvalue 2. There are two important questions. One is the eigenvector unique corresponding to an eigenvalue, and how do we compute eigenvalue and eigenvector? First, quickly see this one. So let us say that lambda is an eigenvalue for the eigenvector x. Now if c is any real number, then you can see that A times cx is same as c times ax, because it's a scalar, it can come out, and ax is lambda x, so this becomes c times lambda x, or I can write it as lambda cx. So here for lambda x is an eigenvector, and here acx is lambda cx, which means for the same lambda, cx is also an eigenvector. It means if x is an eigenvector, then the constant multiple of x would also be an eigenvector, and in that case we can say that the eigenvector corresponding to an eigenvalue would be infinite. Now how do we find the eigenvalues and the eigenvectors? So we know that to have lambda to be an eigenvalue, it should satisfy ax is equal to lambda x. I can either write it down as ax minus, sorry, I will come back to it. So ax okay, so how do we find the eigenvalues and eigenvector? So I know that ax is equal to lambda x. I can write it down as either ax minus lambda inx, where in is the identity matrix, is equal to 0, or you can write lambda inx minus ax is equal to 0. Yes, so I have to introduce the identity matrix, otherwise I cannot subtract lambda x from ax, and this lead me to lambda in minus ax is equal to 0. So it actually represents a homogeneous system of equation. If you see lambda in minus a is some matrix B, then it is bx is equal to 0. So there are two possibilities, either it has trivial solution or non-trivial solution. If it has trivial solution, which means capital X would be 0. So for trivial solution, capital X would be 0, but recall the definition, we want eigenvectors to be non-zero. It means for x to be non-zero, this matrix lambda in minus a should not be invertible. It means its determinant should be equal to 0. If it is invertible, which means if its determinant is non-zero, then we will get x is equal to 0. So for non-trivial solution, I must consider lambda in minus a is equal to 0. That gives me the values of the lambda. So this equation lambda in minus a is equal to 0 is known as the characteristic equation of A. So clearly the eigenvectors are the non-trivial solution of this homogeneous system, and the determinant of lambda in minus a is known as the characteristic polynomial of the given matrix A. So let's quickly try to find the characteristic polynomial and eigenvalues of this matrix. So for the characteristic polynomial, I must consider lambda in minus a should be equal to 0. So only diagonal entries would change. So lambda minus 1, then 0 and minus 1, then 0, then lambda minus 2, then 3, then 0, 0, and lambda plus 5 is equal to 0, 0, 0. So this gives me lambda minus 1, lambda minus 2, and lambda plus 5 is equal to 0, which is the characteristic equation. Lambda minus 1, lambda minus 2, lambda plus 5 is the characteristic polynomial, and this gives me the eigenvalues to be 1, 2, and minus 5. Okay, this is an exercise which you can try by yourself. Now this is what we have discussed till now. So if lambda is an eigenvalue of A, then the homogeneous system has non-trivial solution. Because of the non-triviality, actually we are getting the eigenvalue, and since it has a non-trivial solution, it means there exists a non-zero vector x, which is the eigenvector, such that Ax is equal to lambda x. Also, eigenvectors of a matrix A corresponding to eigenvalue lambda are the non-zero vector in the null space of the matrix. How do we define the null space? So null space is all those vectors for which lambda I minus Ax is equal to 0. This is null space of the matrix lambda I minus A. Now when you talk of the null space, it must have the 0 vector, which is a trivial solution, and because of the presence of the 0 vector, it forms a vector space. Now in this null space, if we just consider the non-zero vectors, they are actually the required eigenvectors. So eigenspace, which is another term for the null space, is denoted as E lambda, which is the solution space of this homogeneous system. So when we talk of the solution space, it covers trivial as well as non-trivial solutions. But eigenspace must have the, if it has the eigenvectors, they must be non-trivial solutions. Okay, so let's try two exercises. One is find the eigenvalues and the eigenspaces, and we also find their basis. So we start with A. So lambda I minus A, if A is 1, 3, 0, 1. So lambda minus 1, minus 3, 0, and lambda minus 1 is equal to 0. This is the determinant, and that gives me lambda minus 1 whole square is equal to 0. It means the required eigenvalues are lambda is equal to 1, 1. For a matrix of order n, there are always n eigenvalues. They may be distinct, they may be equal. So here we have two eigenvalues 1, 1, which are equal. It means I just need to find the eigenspace E1, which is all those x for which lambda I minus Ax is equal to 0. So lambda is 1, so this becomes 0, minus 3, 0, 0. I substituted lambda is equal to 1 here, and x1, x2 is 0, 0. Yes, if you solve it, then the first equation gives you 0 x1 minus 3 x2 is equal to 0. That gives you x2 is equal to 0. It means it is equal to g x1 comma 0, where x1 belongs to R. So you can write, so this is the required eigenspace, and you can write it as a span of 1 comma 0, and it's a non-zero vector, hence linearly independent, implies the set 1 comma 0 forms a basis for E1. Now let's try the another matrix. Let me write it down. So it is 4 0 minus 2 6 2 minus 6 4 0 minus 2. This is matrix B. I have to find its eigenvalues and eigenspace. So lambda I, determinant of lambda I minus B becomes lambda minus 4, lambda minus 2 and lambda plus 2. Then this is 0, this is 2, this is minus 6, this is 6, this is minus 4, this is 0. If you compute it, it comes out to be lambda minus 2 whole square. So the characteristic equation gives me lambda is equal to 0, 2 comma 2. So it means I need to compute E0 and E2. We will compute it one by one. So for E0, it is all those x for which if I substitute lambda is equal to 0, so for which minus bx is 0. Yes, so I have matrix B. So minus bx or minus B matrix is minus 4 0 2 minus 6 minus 2 6 minus 4 0 2 and 0 0 0. Homogeneous system of equation. I must compute its RREF or REF. That gives me 1 0 minus half. Please do verify by yourself. So you can see that there are two pivot entries, and it means that the required equations are x1 minus 1 by 2 x3 is equal to 0 and x2 minus 3 by 2 x3 is equal to 0. So it means E0, if I write it down, so I have the values of x1 which is x3 by 2, I have the values of x2 which is 3x3 by 2 and then x3, where x3 belongs to R. This is a span of 1 by 2, 3 by 2 and 1. So set 1 by 2, 3 by 2 and 1 is linearly independent, implies it forms the basis for E0. Yes, similarly I have to compute E2, so I must substitute lambda is equal to 2. So E2 is all those x for which 2i minus x, so lambda is 2, is equal to 0. So if I write 2i minus b, it is actually minus 2 0 2 minus 6 0 6 minus 4 0 4 and 0 0 0. So this is my 2i minus b. Now you can see that all of the rows are same, so it simply gives me 1 0 minus 1 0 0 0 0 0 0 0 0 0. That gives me x1 is equal to x3. It means my E2 would be x1 is x3, this is x2, this is x3, which is x2 x3 belongs to R. It means that it is a span of 1 0 1 and 0 1 0. Both are Li, which is span S, implies S is a basis for E2. Yes. So I have added the solutions in the slides also. You can see by yourself. All the details have been added. Now next quick observation is, if lambda is an eigenvalue of matrix A and n is positive integer, then lambda raised to the power n is an eigenvalue of A raised to the power n. So this is very easy to verify. If Ax is equal to lambda x, if you multiply A on both the sides, this becomes A square. This is A lambda x, which is lambda Ax, and Ax is lambda x, it becomes lambda square x. So if lambda is an eigenvalue of A, then lambda square is an eigenvalue of A square, and lambda raised to the power n is an eigenvalue of A raised to the power n. For the negative powers, we only need that A inverse exist, then only we can talk of its eigenvalues. So very interesting question. It says that let A be a 2 cross 2 matrix with the eigenvectors v1 v2 and eigenvalues lambda 1 lambda 2. X is any other vector. You need to find A raised to the power 10x. Yes. Now the first thing is, you cannot write A raised to the power 10x is some lambda raised to the power 10x, because it is not known that x is an eigenvector, and for the x, by chance if it is an eigenvector, you do not know what is the eigenvalue. Yes, now how do we approach this problem? So we have given v1 and v2, which are element of R2. It's clearly visible that v1 v2 are linearly independent, hence they forms the basis for R2, and it means that you can write x, which is 5 1, as a linear combination of 1 minus 1 and 1 2. Yes, so I think it comes out to be 3 and 2. Now you can apply A raised to the power 10 on both the sides. So this is A raised to the power 10x is 3, A raised to the power 10 1 minus 1 plus 2, A raised to the power 10 1 2. Now you can see that A raised to the power 10 1 minus 1. So 1 minus 1 is an eigenvector, and therefore A raised to the power n v is lambda raised to the power nv, and lambda, corresponding lambdas are known. So this becomes 3 minus 1 raised to the power 10 1 minus 1 plus 2 raised to the power 10 1 2. Yes, so this gives us the required A raised to the power 10x, which is 20514093. Yes, so very interesting question. So this is an exercise which you can try by yourself. A raised to power 25, you need to find its eigenvalues and the basis for the eigenspace. A quick observation is, a square matrix is invertible if and only if lambda is equal to 0 is not an eigenvalue. Yes, so you can see that how do we found the eigenvalues. We consider the characteristic equation A minus lambda I, determinant of A minus lambda is equal to 0. So if lambda is equal to 0, you will get determinant A is equal to 0. So lambda is equal to 0 implies, if lambda is equal to 0 is an eigenvalue, then determinant A is equal to 0, which means that A is not invertible, and which also means if lambda is equal to 0 is not an eigenvalue, then A is invertible. So this is what we can summarize. We started with A is invertible, and you can recall all these results, and with the previous result we end with lambda is equal to 0 is not an eigenvalue of A. So that's all from this class and from this course. Thank you very much for watching.